Welcome to the CAD for Assurance panel. This is the panel 5. Before the panel, I would like to introduce our effort to promote hardware security and the CAD for Assurance related research. So as many of you may already be aware that the CAD for Assurance website was established in October 2020. And we have 4 organizers, Swarup, Bhunia, Ankur, Zhongyu Ho, and myself. So since the start of the CAD for Assurance website and the panels, as well as demos, webinars, we have attracted a lot of attention from all around the globe. And the number showed here is a bit outdated because it was reported early this year. And then we will adding these numbers should be increased significantly in this year, given that the CAD for Assurance events have attracted even more attention. Next slide.
Can you see it here?
No, yes, I can see it. So we would like to thank our sponsors. They are the IEEE CEDA, IEEE HSTTC, Hardware Security and Trust Technical Committee, UF, the NELMS Institute for the Connected World. And also we would like to thank 3 companies, Mercury, Northrop Grumman, and Huntington Ingalls Industry. But I would like to emphasize that we actually received a lot more requests who would like to support our events. As Swarup may mention, that this is our kind of like voluntary effort. So we did not take any fundings from those sponsors. These are all the effort and what they've been spent to promote the whole hardware security community. And in the future, we will definitely welcome more to be listed here. But for now, we temporarily keep the sponsor list as they are. Next slide. So just one quick advertising that in 2 months, we will have more tool demos. And actually, there will be 2 tool demos, not just this one. Feel free to go to our website, cadforassurance.org, or the IEEE CEDA website to check the latest webinars, panels, and the tool demos. Next slide. Okay, so again, this is a society that we welcome all your support. And without the researcher support, we cannot achieve this this level, I would say. And this is the society that we have been building to promote all hardware security related and CAD for Assurance related tools, benchmarks, and also some ideas through these panel discussions. So please feel free to contact us if you are interested to contribute to this community. Either you have tools to deliver or you have some opinions you would like to share with us, with the whole community. So we are here to support all these events, all these activities. Our goal is very simple. We want to promote the whole community and to protect our hardware infrastructure. Next slide. Okay, here we go, the most exciting moment. I would like to introduce you the 2 moderators, Professor Swarup Bhunia from University of Florida and Professor Ankur Srivastava from University of Maryland. These 2 are very famous professors in the CAD for assurance and hardware security community. And I assume that all of you know them very well, so I don't need to re-emphasize how significant they are and how much effort they have been spending to support the community. And now I will give the podium to Ankur and Swarup.
Thank you, yeah, really appreciate that. I don't know if we are that famous, but we'll take it. So Ankur, please go to the next slide. Okay, so what we will do, myself and my co-moderator, Dr. Ankur Srivastava from University of Maryland, we will introduce the topic and then we'll give it to the panel to share their position statements or point of view on this topic. As you can see from the title of this topic, it's pretty broad in its scope. We are talking about hardware assurance. We're talking about AI. In particular, we're looking into the hardware implementations of AI or AI acceleration through hardware. And we are trying to see what are the interdependencies between these two areas and what are the conflicts. Are they friends or are they foes? So we'll bring some interesting, exciting questions relevant to this topic, and we will let the distinguished panel answer that. Of course, like any successful panel, we would be looking forward to having active engagement from the audience. Ankur, go to the next slide, please. Okay, so before I introduce the topic, I would like to talk about the panel schedule. It's a 90-minute panel, and about 15 minutes of that would be introduction of the topic and the panelists by the moderators. And then followed by that, we will have position statements by the panelists, and these panelists do encompass different areas of expertise. They come from different background, and as you will see from their comments, they do cover different areas of expertise, and I think their viewpoint would be as diverse as you can think of, and they will come up with strong opinions on these particular topics. We did not bias them. We didn't ask them to choose any side because the topic is a question, as you can see, and I didn't ask them to take any side. So they will probably come up with their unbiased opinions on this topic and share their viewpoints. After that, we will have a question answer session, which will be about 35 to 40 minutes, depending on how long the position statements go. And during that time, we would be looking forward to your active engagement. So please feel free to ask questions, whatever you like, and we'll let the panel answer those questions in first come, first served basis, in that order. And finally, each of the panelists would be asked to give a closing remarks about 1 to 2 minutes on this topic. So Ankur, please go ahead. Click on more time. Yes. So if you would like to ask questions, you need to use the Q&A feature of Zoom. I guess all of you know how to use that. If you have any problem, please post a comment in the chat box. So that's how you ask questions. And as I said, we will take them one by one and let the panel answer those questions. Now, let me briefly introduce the topic. Of course, the panelists would have a lot of details on different perspectives, covering different perspectives on the topic. But we have few slides. Myself and Ankur jointly made those slides to give you a brief introduction on this topic. With that, Ankur, can you go to the next one? So if you look at the modern electronic hardware supply chain, as you know, it's extremely complex, globally distributed, and it does involve multiple untrusted parties. And that makes the equation very interesting. Because of that, through the entire life cycle of electronic hardware, and on the right-hand side, we are showing you a very simplified, highly abstracted version of the electronics life cycle. And it goes from IP vendors providing the intellectual property blocks. It goes to typically a system on chip design house, which will basically create the design and make the GDS file, which will go to a foundry test assembly facility and will be manufactured there. And finally, we'll make the system and deploy in the field. During this really complex, long life cycle, there are many different attacks that can happen from different parties on different model of hardware. right? As you all probably know, it can happen. It can have hardware Trojan insertion, hidden backdoors. The IP blocks can be pirated, cloned, and there might be side channel attacks. There might be probing attacks, row hammer attacks, and many more, encompassing the entire life cycle. What makes it more interesting, as I said before, is that because of the fact that there are a lot of untrusted entities in the long complex life cycle, which leads to this evolving zero trust model where you assume pretty much every important stage of the life cycle can be completely untrusted, particularly the foundry, test, and assembly are generally considered untrusted. Then establishing trust of the hardware with the assumption that a lot of these facilities and people and tools and IP blocks can be untrusted is a very interesting problem statement. How do you come up with trustworthy hardware under the assumption of zero trust? That's a very, very important question which the research community is trying to answer. Now, the point is that how does AI come into picture here? Now, it turns out, if you click a couple of times, if it turns out that electronic hardware is subject to a lot of different threats, as you can see here, but turns out that the power of AI can be used to address these threats significantly. And in the next slide, we looked at the literature. We did spend quite a bit of time to figure out how the AI is being used to deal with these problems of hardware assurance. And when you talk about hardware assurance, we're particularly focusing on the security and trustworthiness of hardware. It turns out that AI can be used to do a lot of different things to enable trustworthiness of hardware. It can be used to explore the attack surface. It can be used to create attack signatures and identify them. It can be also used to predict unpredictable attacks and look into the future attack instances and how we can defend them. So on one hand, it can be used to explore the attack space. On the other hand, it can be also used to come up with design verification solutions to deal with those attacks. So looks like AI can be significantly helpful in terms of dealing with these diverse attack surfaces. So if you go to the next slide, there is another interesting side of that coin. I'll not go into the details about that, but it turns out that if you click one more time, Ankur, the AI can also bring in a lot of important problems. So as I said, AI can help on one side. On the other side, if you look at the AI hardware, go back. Yeah, if you look at the AI hardware, it does bring in a lot of interesting problems itself. And these problems, and this is a slide I took from Rambus, these problems do span from the implementation of AI algorithms in hardware, which is typically called hardware acceleration of AI, to training data, to the inference model, input data, and endpoint hardware. Encompassing this entire life cycle of AI computing environment, there are a lot of interesting security and trust issues, and they span hardware root of trust. Typical AI computing systems do not come with hardware root of trust, so that creates a problem. There are problems with IP security of the inference models, algorithms, training models, and training data. There are problems with information leakage. There are problems with data and model corruption. So there are diversity of problems on the AI hardware itself. And I put a quote here from Bart Stevens, which is a product marketing director in Rambus. He basically said that many AI and ML models today do not have security built into them. They are mostly focusing on the processing power, but not security. So that means that AI intrinsically have a lot of security problems. So that does conflict with the fact that if you have a system with AI computing built into it, then overall security and trustworthiness of the system can be impacted by the security and trust issues of the AI hardware itself. So we'll look into these questions, and the panel would be able to provide their viewpoints and answer your questions on this really diverse and deep and exciting topic. So with that, I will hand over to my co-moderator Ankur to introduce the panelists and let them give their position statements.
So, good morning, good afternoon, and good evening, everyone. Thanks a lot for joining as audiences today. And I'd also like to thank, along with Swarup and the CEDA folks, all the panelists who are here today for their valuable time and opinions and ideas. In order of last name. So Mike Borza from Synopsys. Mike is a Synopsys scientist working broadly on security in integrated circuits and systems at Synopsys Incorporated. He has more than 25 years of leadership and technology experience in security and safety critical systems engineering. In 2002, he founded and was the CTO of Elliptic Technologies, acquired by Synopsys in 2015. His previous experience include Chrysalis ITS, now Thales, and Carry, HID Global, and Alcatel Transport Automation, Thales Transport. He is currently Vice Chair of the Accelera IP Security Assurance Working Group and is a principal investigator in the DARPA ACE program that many of us are also collaborating with him on. Vivian Kammler from Sandia National Labs. Vivian is an R&D manager for cyber systems assessment at Sandia, where she has served for over 20 years. She has shifted her focus from design to verification to hardware assessments of microelectronics-based systems over the course of her career. She now uses this experience to benefit digital and cyber assurance initiatives in her organization. She received her Bachelor of Science in Engineering from Harvey Mudd in 1997 and Master of Science in Computer Engineering in Northwestern in 1999, when she and I had the same advisor at Northwestern when she was pursuing her master's and I was pursuing my master's too. Brian Knight from Microsoft. Brian Knight is a principal product manager for autonomy, space, critical industry, and innovation, ASCII at Microsoft. He concentrates on incubation and innovation programs, building transformative technologies for mission engineering in autonomy, space, spectrum, silicon, AI, modeling, and simulation. Currently, Brian is supporting a team developing powerful AI tools to help innovators with information discovery and contextual assistance to spur creativity and invention. He is also developing strategic solutions in hardware supply chain security to ensure the confidentiality, integrity, and provenance of microelectronic systems. Len Orlando from AFRL. Len serves as the OST-TNAM Quantifiable Assurance Simulation Lead, contributing to the DoD's renewed interest in state-of-the-art microelectronics for national security, and was recently appointed to lead the AFRL Sensors Directorate, Aerospace Components, and Subsystems Division on Digital Engineering Transformation line of effort. Earlier, he has served as the Air Force Hardware Assurance Lead for the Office of the Secretary of Defense Trust and Assurance Microelectronics Program, the OST-TNM Secure Design Thrust Area Lead, and the OST-TNAM Education and Workforce Development Co-Lead. Sam Weber from ONR. So Sam is a program manager at the Office of Naval Research. Earlier, he was a faculty member at both Cornell and the University of Pennsylvania, and then spent more than 11 years as a researcher at IBM T.J. Watson Research Center. For almost 4 years, he was program director of the National Science Foundation's Secure and Trustworthy Cyberspace and Trustworthy Computing programs. He has experience in both academic research and more immediately practical endeavors. His recent research focus has been on software engineering for secure and reliable systems. So a very illustrious panel, and thanks a lot for serving and serving us with your time. These are some of the seed questions that we will pose to the panelists, after they have presented their position statements on the primary theme of this panel. So I'm going to let you as panelists present your ideas, and then we'll come back to these seed questions and also answer questions that the audience may have. So I suppose, Mike, you are next.
Very good, Ankur. Thank you very much. So I guess I'll just open with a few comments about my thoughts on the use of AI and ML today. Really, it's I view it as a tool, and it's like a very sharp knife, scalpel. And so if I take that approach, then most tools can be used for good. They can be used for evil. And we're seeing that happening right now. Beyond that, the AI ML's systems are open to attack. And this is exactly what Swarup was just talking about. It's, always the case that functionality comes first. People try to innovate with something that produces functional results as quickly as possible without stopping to consider the consequences of that or the vulnerabilities that may be inherent in that. And so we're seeing that's the situation right now, simply because AI and ML in its current guise is changing so fast, and the development of the functionality is moving very quickly. So on the positive side, there are really great opportunities to capture and systematically use existing knowledge about security of systems. And so encoding that in an AI is a great opportunity. And we're starting to see some interesting uses of that. So things like verification of systems and chips and even smaller pieces of IP, seeing AI-driven penetration testing, red teaming, as well. Assurance coverage is something that I think is going to emerge as a viable use of AI, and one of the great uses of AI. And of course, when you can use a computer to do something that is inherently difficult and involves a lot of drudgery to look through vast reams of data, it's always a good use of the computer. So we take human knowledge encoded in the form of some AI and ML algorithms, and then apply that over and over again in a systematic way. That's a great use of the technology, I think. I think we're going to see in the future sort of AlphaGo style attack and defense learning being applied here, and some of that's going on already. Aggregating and extracting attack indicators from data over large populations of chips and systems is another thing that I think is going to emerge in the future. And so we're just starting to see people trying to apply that, but it's really early days, and I think there are really a lot of opportunities for that kind of thing. On the negative side, then any kind of tool that behaves as an adversary or can be used to attack something can obviously be deployed for that explicit purpose. AI and ML systems themselves are vulnerable to attack. There are all kinds of interesting attacks, training data poisoning, model extraction, and the direct corruption of the models themselves are all opportunities. There's a very large attack surface because of the way we deal with AI for very large problems, and that is that the data is collected by online devices. It's returned to a data center where it can be aggregated, and the models built from that, and then the models themselves deployed back to the edge devices that can use them in at least distributed AI. Other kinds of AI are strictly data center centric, and there you have still large swaths of the data center that are involved separately in the learning and subsequent use of the models. And so the attack surface is large, and that means that we're going to spend the next several years learning about what these attacks are and how to reduce our vulnerability to those kinds of attacks. And finally, AI systems are brittle and extremely nonlinear. And so when they break hard, and that creates all kinds of opportunities for attack. And people try to use anomalous data or data that is not part of the training set to drive behaviors that they can reliably use to take the AI out of its intended operating point. And so these are some of my thoughts about what we're talking about today.
Thanks a lot, Mike. So Swarup, I suppose I should move to the next speaker.
Yes.
Right? Okay.
Yeah, absolutely. Let's do that.
Okay, so the next speaker is Vivian Kammler from Sandia. Vivian.
All right, I'm guessing you can hear me okay.
Yes.
Thanks everyone for inviting me to the discussion today. You already know hardware assurance is an area I care about, especially given the core mission of my employer of 20 years, Sandia Labs. For the rest of the audience, Sandia is a federally funded research center, development center, government-owned, contractor operated for the Department of Energy. And that distinction that it's the Department of Energy instead of the Department of Defense is attributed to our roles as stewards of the nation's stockpile, nuclear stockpile. So I know a lot of folks on the panel and everyone in the audience can say they care about hardware assurance, but I care about it for our nukes. Okay, so that's not the only space that we work. Those responsibilities cover about 55% of our budget, but there's a lot of modeling and simulation, emulation, and analytics that we built up around that core mission. When I hired on, it was after 9/11, so Ankur knows this. The labs were expanding their role in national security. So first, we were looking at digital signal processing applications and satellite systems and military GPS systems. And just to touch on one of those seed questions is we had metrics. And that made formulating the problem so much easier. It made working with industry and academia so much easier, and the day-to-day job, because there was power, area, and performance. And that was a focal point for optimization. Okay, you can generate a lot of papers on that. So it allowed us to measure progress. It allowed advancements in the commercial EDA tools and innovation, right, in design and applications. But we know, and Swarup spoke to this, that they don't measure hardware assurance. And at the labs, we're pretty black and white about many aspects about supporting the nuclear deterrence. You have to care a lot about always, never principles. To be an effective deterrent, you always want to be available and ready to perform when authorized. And for the sake of public safety and our standings as stewards, never when it isn't authorized. So we turned our energy towards hardware verification and pounded that. At least we can take care of the integrity piece. But given the tools that we had and pushing harder and harder in the limits of modeling, simulation, and formal verification, which is our best friend, we had to use functional coverage to handle our hardware assurance metric. If only you can master that art of articulating those requirements properly. And that's really still true of hardware security and assurance today at a very, very high level in practice. So for us to uncover and mitigate more unknowns, we need more assessments, right? And more R&D filling into those gaps, but it keeps getting more and more complicated, more time consuming, and importantly, much more expensive. And right now we're looking at weapons in the stockpile with an average age of about 26 to 30 years. So where is that new equilibrium point? So from my perspective, AI is what it is, friend or foe. Doesn't really care about my feelings about it anyway. But I'm going to go ahead and play the game and anthropomorphize it. Okay, AI, it's hungry for data. We have small volumes. Okay, and we're really, really protective about our information. Okay. So that's not going to help AI. AI also needs room for forgiveness. It can't provide that 0.99999% true positive or true negative rate that we need to converge on checking off those always never requirements. So we need to find a better home for it, perhaps more human in the loop than hardware in the loop. So I'm thinking risk assessments, detection and sensing, forensics, and incident response, because always never is necessary, but we can't apply it to every aspect of our work. Complex environments and threats, they demand complex responses and protections. And we don't want to go extinct with the dinosaurs. We'll depend on networks, clouds to access information. We feel the pinch from global supply chains and disruptions in that supply chain. And even though we're an R&D facility, we still have to deliver product on time and within budget. And we need these parts to do that. And we can't always depend on human intelligence and luck and human heroics to differentiate what's good from bad. So as far as the new metrics, time and money still work to measure our pain points and progress. And there's lots of room to optimize amid scaling problems, the manual processes, and right now demands for flexibility and responsiveness. So in those cases, AI is starting to look more like a friend, but does that mean we're ready to trust it? Anyway, thank you, and I'm looking forward to your questions and to the discussion today.
Thanks a lot, Vivian. We'll move on to the next speaker, Brian Knight from Microsoft. Brian, it's a go for you.
Sounds great, thank you. And I do have some slides, so if you could please forward to those. Thank you very much. Appreciate IEEE and CAD for Assurance community for hosting this event, and I certainly look forward to the learnings I've received already, and certainly the insights that will be forthcoming from the panel and the Q&A session. With that, I'd like to introduce the subject with some comparative data to start. Next slide, please. And you can go ahead and build this out to the 4 elements. Thank you. So if we consider complexity and growth and transistor count and parameters in kind of the modern AI models, you know, the Apple M1 Ultra, for example, has about 114 billion transistors, and we can kind of associate that with the human brain having roughly the same number of neurons. And the Wu Dao AI model is at about 1.8 trillion parameters. It's one of the largest models in the commercial area at the moment, and the human brain has, you know, up to 1,000 trillion synapses. Now, I'm not attempting to make a conclusion on the basis of this data, but it's a good thought exercise to consider how much complexity and growth has occurred in these domains. Next slide, please. So considering this thought exercise a bit further, you know, while these charts don't include kind of the latest examples that I just highlighted, they clearly kind of show the rate of growth in natural language processing models and how that's, you know, certainly outpacing transistor count. And this kind of begs the question of that, given these emergent complex AI models, how can we best apply them to solve real world problems such as hardware assurance? And hopefully today, you know, in our discussions, we can start to create some clarity around some practical approaches forward. Next slide, please. So as a first step, I thought, why not ask an AI system about this problem domain specifically? So using kind of the OpenAI DALL-E 2, which creates realistic images or art from natural language, I inquired about visualizing hardware assurance versus AI. And you can go ahead and build out the slide. It's 3 images there, and you know, I certainly don't recommend testing these ideas in the real world. You know, prying up a QFP with an open-ended wrench probably isn't a good idea, but you know, perhaps these images are telling us that hardware assurance and AI is still very much a work in progress. Next slide, please. So there have been some fantastic applications of AI and in particular machine learning to support hardware assurance, as shown there on the left. And many of these applications I'm sure we'll discuss today. If you can click one more time, my interest is really ensuring that these AI systems and tools that are created become measurable and can be evaluated across these elements on the right. Training strategies, model complexity and performance are relatively mature, but when we start to look at generalizability and model robustness and computational cost, scalability, and especially explainability, These are much more nascent measures for domain-specific applications, but certainly critical for adoption. And as some of the panelists have already mentioned, really foundational to everything that's delivered is this application of responsible AI principles to ensure wide adoption. Next slide, please. So in closing, I'd like to kind of list a notional set of starting challenges. We certainly need open data sets and models and tools to create a vibrant R&D community. I believe transparency in AI-driven design decisions is critical for us to understand hardware insurance impacts. And fundamentally, I think we must shorten the development to product cycle times, and hopefully, with the additional AI workloads optimized on cloud compute hardware, we can achieve that. And finally, I think AI-driven hardware assurance certainly can enable kind of a new ecosystem of analysis tools across security and compliance and lifecycle monitoring. And I think this, has an opportunity to create some new revenue models across that end-to-end value chain. And I think this will be certainly a key incentive for industry to adopt AI and hardware assurance. Next slide, please. Thank you. And with that, I'll certainly turn the program over now to Len Orlando from AFRL for his introductory remarks.
Thank you. Thank you. I'll request Len to present his thoughts. Now, Len, you did have slides, I believe, and the same protocol.
Yes, I did. Thank you very much for the introduction and an opportunity to speak with you this morning. If you go ahead and go to the next slide. So I wrote the set of charts today around using AI in the development of microelectronics to accelerate our ability to be more efficient. If you read Outliers by Malcolm, he's described this context of needing 10,000 hours or 10 years of practice at something to become, a highly effective or, an outlier, right? Be those that are gifted in that realm. So I wrote this from the context of we use AI and machine learning as to accelerate our ability to comprehend very complex systems and to be efficient in their use. Because the complexity and scale of the problems is exponentially growing. And so from Air Force and DoD perspective, what we want to have the ability to make intelligent decisions based on the data that we have available to us to manage, cost, schedule, and risk. And some of the key points that I've highlighted for you there is the production, being able to drive the solutions in a more efficient manner, and then abstracting and automating the complex systems that we have in front of us. The other piece that the introductory statement makes is the ability to bring more individuals with a diverse set of backgrounds into this community for both AI, machine learning, and microelectronics, because there's a lot of desire to produce hardware, but not necessarily a lot of capable individuals to do that. So using these systems to complement them is a very effective way for us to bring more people into the fold. Next slide, please. The challenges with the Air Force systems in particular is the fact that we operate in a very diverse environment. We have systems that may be operational for 50 or 100 years. We have to operate in space as well as in contested environments. And so we have challenges around resiliency, high bandwidth, so performance, need to make quick decisions when we're in contested environments, maybe on very small platforms that have limited capability. And so looking across the domain, we have a very varied set of complex challenges, and they're mission unique. And then simultaneously, you have microelectronics and cyberspace on the left side of that slide that are kind of ubiquitous across all of those platforms that we have to be concerned with. If you can go to the next slide, please. And in general, the Air Force is adopting microelectronics and new technologies because we're operating in domains that we couldn't do before, right? We would not be able to stabilize some of our systems without microelectronics. A human could not fly those systems by themselves. And then we're also removing the human completely from those systems and operating remotely. So the use of AI machine learning to complement the human is already existing in our systems in this kind of R2-D2 style of companionship that we're seeing with AI machine learning. Now, that doesn't necessarily address how we secure those systems, how we assure those systems that they're going to work correctly. It's still a very performance-driven perspective, but it's how do we augment the human with AI and machine learning broadly across our weapons platforms. Next slide, please. And then kind of redirecting to the microelectronics domain. Swarup did a very good job of highlighting the various stages of microelectronics development, and this one here is kind of unique to the DoD, only in the sense that as you look kind of left-hand side and move to the right on the top graphic, we have the distillation of very high-level requirements and specifications down into the design and verification space, and so you can kind of think of the temporal aspect of the design and the opportunities for AI machine learning, which I'll go into in the next subsequent slides, but you also have it into the implementation stage. And so what I did here is I kind of married those two concepts and overlaid the fact that, if you look at the Industrial Revolution, what has occurred is we've gone through this revolution of automation, and now we're moving into this automating of the automation, which is the Industry 4.0. And so what I'm seeing in industry in total is the migration into how do we use our already scripted environments and the EDA tools, design and technology. How do we leverage that and use these other tools to integrate and effectively use all of the diverse sets of capability available to us to basically move into this Industry 4.0 mindset. Next slide. And then I kind of walk through the different areas that I thought AI machine learning could be applied. I mentioned requirements traceability. That's a big one for the DoD, being able to link that from a protection perspective or requirements up front in the contractual language through our diverse set of suppliers into these models. And so there we'd be looking at more of the anomaly detection, surrogate modeling, areas where there might be gaps in our data or in the available data that we're using to make these intelligent decisions. And then as you kind of move towards the right, the predictive analysis and maintenance, when we have complex systems, decomposing those or managing composed systems is a part of it. So, when we had more data, that's great. Access to the data is even better. But really what we want is the combination of both of those, but having high quality data available to us. And that kind of mitigates some of the potential threats when we're talking about high quality data. But then there's the definition of what is high quality. And so that's still an area of learning for, I think, everyone on the panel. Next slide. And then this kind of dives into the implementation, right? So as a designer, where are the opportunities for AI and machine learning? Where does it provide us a strategic advantage when we're balancing the complexities of the design itself and the architecture, the EDA tools, which have gotten incredibly complex, and then the technology nodes as you move towards advanced state of the art. And so utilizing AI machine learning to act as act as a way to orchestrate all of these different things is where we're going towards. And then also as a buffer to mitigate some of the commercial or proprietary data that would potentially be unavailable to us as a mechanism to help us gain access to the data without exposing anything that might be company critical or mission specific. So it ends up being a strategic advantage for us in general. And next slide. And then finally, the DoD typically manages everything in terms of risk, especially in the security domain. It's a combination of how much does it cost and what does the risk profiles associated. And these are just some examples of various different security domains that we're looking at that could potentially feed into a zero trust engine and help us manage that risk so we can be make those intelligent decisions when it comes to security. And here I'm using security and assurance kind of interchangeably. They're very complementary, even though they have different aspects that you're looking for. And I think that's the last slide for me this morning, and look forward to the discussion this afternoon or following. So thank you.
Thanks a lot, Len. Thank you very much for elaborating your thoughts from the government perspective. So I am not able to, so the last panelist is Dr. Sam Weber. Let me just go to his profile. So Sam, you're next.
Thank you. So first of all, my lawyers say that I have to say that I'm speaking on personally and not on behalf of the Office of Naval Research or the federal government. Okay, so my position statement is primarily that there is no silver bullet. There's no royal road to hardware assurance, and there's no substitute for very good engineering. So if you notice, I have enough white hair to have experienced a number of research fads over the years. And what the common pattern is that there is a high level of enthusiasm in the community, which grows and then usually collapses at some point. And AI is certainly one of the current research fads. So what's happening is that people say, hey, AI can do these amazing things. I mean, you could give pictures of a cat and dog and tell the difference between them. Or you can tell it, say, give me a picture of monster in a bowl of soup, and it'll come up with a picture. And people go, oh my God, I have no idea of how to program that. This is amazing. And we can use this for hardware assurance. And so people are very enthusiastic. Unfortunately, if you notice that telling the difference between a cat and dog and drawing pictures of monsters in soup are all things that 2-year-olds can do. And of course, we don't expect 2-year-olds to be able to solve hardware assurance problems. And I'm sure that people are ready to put a lot of nasty comments in the Q&A chat, but it's not that negative after all. I mean, basically, the reason why something is a fad is because there's a nugget of something good in it that people catch on. And the standard isn't that this thing should be able to be a miracle cure for everything. The standard is, can this help people? And so one of my frequent examples is checklists. So checklists are very, very dumb. They're just a list of tasks, and you force people to check them off as they accomplish them. And yet this simple thing, which is entirely brain dead, has probably saved hundreds of millions of lives over time, because people are really bad at being methodological, and they just sort of get distracted and forget things. And in a hospital setting, being methodological, make sure you've asked the right questions, ends up saving lives. It saves engineers from making mistakes, and it's very useful, even though it's completely dumb. And AI similarly can do things that people are not very good at. I mean, people are not very good at keeping, at going through amazing amounts of information. They're not good at repeating a task. They get distracted. And AI is very good at pattern matching. It's very good at dealing with volumes, etc. And another comparison is with formal methods. For formal methods, they're also another method that people have developed to augment what people are naturally bad at, thinking logically, going through formal mathematical statements. And yet, and people are still use formal methods for hardware assurance, and they should. But in the last Oakland conference, there was a paper about security bugs in systems which have been proven to be secure. And so they showed a lot of security bugs in these systems. And the speculation is a lot of them came up because what people did was use formal methods instead of engineering. That they basically thought, okay, I've proven this to be secure, therefore I don't need to go through my usual engineering processes. And the result was security bugs. And so I think but you still need again, you need to do form methods but you can't use them as a replacement for engineering. Similarly, in artificial intelligence, you can use artificial intelligence to do things that people can't do very well, pattern matching, and going through huge amounts of data, and etc. But you can't use them instead of engineering. You have to use them, like Glenn said, as a companion, an existing tool. And so I think that there's a lot of good things that come out of using AI, as long as you don't expect it to be a cure-all, and instead emphasize the engineering aspects and use it properly. Thank you.
Thanks a lot, Sam, and thanks to all the panelists for their insightful thoughts and ideas. So we have a set of seed questions, but I would first invite some of the audiences to pose their questions. And I am wondering how I can get access to those questions. Yeah. So there's so Swarup, can you hear me?
Yes. So thank you, Ankur. So we have collected a set of seed questions, and by the way, these questions are kind of a curated set of questions that came from people which we communicated to. When we started advertising for this panel, we got a number of questions from the prospective attendees ahead of time, and that was pretty unique. Some of the questions came from industry practitioners and some of them from academia. So these questions are collected set of questions from the attendees as well as from the organizers. So we can pick those questions, but of course we would like to give priority to any live question you might have. So please type your questions. We see two of them are already posted here, and thanks Vivian for addressing one of them. There is one remaining question in the Q&A window, but we would definitely look for more from the attendees. While you're waiting for more questions, Ankur, yeah, go ahead.
Should we read the question, Swarup?
Yes, maybe we can read the question and then we can let the panel answer that one. While you're waiting for more questions, we can pick up any of these seed questions.
Okay. So let me read the first question in the Q&A, which is from Prabhuddha Chakrabarti. Is transparency good or bad for security, especially considering the fact that AI models can learn to attack from too much transparent data? That's a question, I guess it's general for AI, but specifically in the context of hardware, what would one think?
Right. I think the higher level question, probably, if I may add to it, is that so AI provides opportunities to add transparency to the models and the data, as well as AI also is looking for more explainability. The question is that, do they conflict with the security requirements? So transparency and explainability of AI, are they at odds with the security of AI? Anyone can take that from the panel.
So in some respects, transparency is going to, well, you know, it's going to exist regardless, because people have become very good at reverse engineering and analyzing physical systems that are sitting in front of them. And the more access you have to that system, the more transparent they become. So in that respect, you know, the tendency of people to try to obscure what they're doing falls away as more and more better and better analytic capabilities come available. And with those, you know, comes the ability to apply AI to those, to the understanding of those. But, you know, we still see for different commercial reasons and also for other kinds of reasons that people prefer to try to keep their security systems opaque as much as possible, not be too transparent about them, simply to slow down the rate at which they have to deal with those kinds of attacks. And, you know, this is true in the commercial world. It's true in the, say, the government and aerospace and defense communities. It's true generally. If you look at some of the standards around, especially security, things like common criteria say that designs should not be transparent. They should not be open and available to adversaries to try to attack. And that's part of the criteria that they measure against, in spite of the fact that, you know, there's this countervailing opinion and tendency to try to make systems open and transparent. So, you know, I say that you still want to try to slow things down as somebody trying to build secure systems, which, you know, flies in the face of transparency.
Thank you, Mike. Any other perspective? Any other quick one?
Yeah, I might. Sorry, go ahead, Vivian.
I need to stop playing with the Q&A here because it keeps moving questions into the answered bin when I haven't had a chance to respond. But so
that's
one
an
area
AI problem. That's an AI problem.
Yeah, exactly. So where we see this a lot is when we try to interact with academia or industry, right? We want to support R&D and like our fab data, for example. We have to, we feel that conflict of, is it okay to share this? We want to be able to do data analysis on it and do real-time real-time reactive processes to be able to respond to any kind of anomalies that are detected along the line. But then there will be that open question of, well, can we share this data? So in that case, we do feel that conflict, but we would really need to understand more in order to be able to have that open sharing of data. So I think we're going to have some tiered approach here for what data is okay to share versus what we just don't know enough to take on the risk.
Thanks a lot, Vivian. There's another question by John Barris. Comparisons with human brain must be done with great care. I'm reading the question in case you don't want me to sort of let me know, but maybe it's a good idea to read the question. So I'll read this one. Comparisons with human brain must be done with great care. Why? The computation model is very different. That is impulsive. The brain does knowledge representation and reasoning in an integrated fashion with machine learning. This is missing in most current works in the, once again, the general context of machine learning. Despite the fact that there are hardware especially suitable for KRR. I don't know what KRR is, but John, if you want to just add another clarification, that would be nice. But I think the spirit of the question is, can we redesign hardware to match these principles, as in principles inspired from the human brain, and examine their assurance and reliability against attacks versus similar behavior of human brains. I think the larger question is that how much inspiration can we take from biology in designing knowledge systems, right? And one of the questions that, like, a lot of the discussion today was about use of AI for hardware design, but a lot of hardware that is being designed is doing AI, right? And the question is, what is the right type of approach of assuring and guaranteeing trust and reliability and safety and resilience in hardware that does AI? And any thoughts from the panel would be helpful.
I'm pausing because I was hoping one of the other panelists would jump in here, but
so let me kind of add a
at least
context.
the third time in my career that AI has been the savior of all things, and we've seen this many times. I think back in the 90s, a researcher at MIT characterized artificial intelligence as natural stupidity. The kinds of neural networks that we're seeing today are very different from human neural processing. And we're seeing a lot more essentially digital signal processing being applied to the problem. And we're seeing networks that are very different from what we think human intelligence or biological intelligence looks like. The other aspect that's very different is that we're operating on integer data at increasingly low resolution, which is one of the reasons that some of the computation is brittle. And by necessity, natural intelligence is done using analog computers, or at least analog elements that behave as the neurons in a biological intelligence system. So the comparisons are, I think, fraught with a lot of danger, at least trying to, as Vivian said, anthropomorphize what AI in machine learning is doing versus what natural intelligence does. So I think the models are just very different right now. I think we'll start to see maybe more convergence as you get larger and larger networks that are hugely interconnected, sort of at planetary scale.
Thank you. Thank you, Mike. So Orlando Arias says, apologies for the three-part question. What are the funding opportunities for research institutions in this domain? Are there any shared industry academic institutions projects that we can participate in? Are internship opportunities for both undergraduate and graduate students with potential industry and government institution partners? I think there was another question, similar spirit raised before. And as academics, of course, we are always looking for new sources of funding. So the larger question really is that in terms of investments by the industry in growth in this area and investments by the government, most notably the federal government, in research in this area, what is the excitement do you see as panelists, and how can some of us, including many of those who are in the audience, engage with you?
So this is a question which we have received from many of the attendees earlier. Maybe some of you can answer that.
And no commitment expected.
Yes.
I mean, I can certainly talk about maybe an academic opportunity. I don't have visibility on kind of funding opportunities in the R&D pipeline, but certainly happy to promote kind of an IEEE opportunity for academics who have interest in collaborating and building ML models to support ideas such as counterfeit detection. I think those who have interest in this domain certainly should explore kind of the IEEE host microelectronic security challenge. We just completed that a couple of months ago and had a supply chain security track to really analyze optical images, build models, and look at security analysis across various components. And we anticipate a very similar competition to take place at the Host 2023 event in May. So please stay tuned, and we'll certainly release some details on how to participate and access some of the data and models early on.
Hey, Brian, if I may, do you think Microsoft and other companies would be interested in hiring students? That's one part of that question, as intern or full-time employee in this area.
Certainly. I mean, we have quite a bit of work in the AI model development, and across a variety of different facets, from kind of the more traditional use of information discovery and contextual guidance in kind of traditional tools that a knowledge worker may use. And then, we're exploring, other aspects of AI for use in mission engineering aspects, to include kind of supply chain security, analytics, and other elements such as that. So certainly interested in students and as well as internships in that domain.
I think
Thank
if you
you.
look at, say, the private sector funding for these things, most of it's going to come from internal R&D development. Synopsys is doing a huge amount of development of tools for different aspects of design and verification, and general supply chain assurance. We've talked with several other companies that are doing likewise, and we're partnering together with some of them on those aspects. I think one thing that's done is say venture funding or those kinds of funding sources for things like AI chips. That's basically over now, and you're going to see funds drying up there. The cost of developing those chips is very, very high, and the number of people who can do it well, even some of the companies that have started up to do this stuff are producing so-so results. And so you're going to start to see things collapsing down to coalesce around a few companies doing that stuff. But the real opportunities of these big system opportunities to use techniques for AI and apply them to different problem spaces. And I think that's where you're going to see most of the funding. So that's where I would be looking.
Thank you, Mike.
Yeah.
Thank you. I think we should stick to technical questions as well.
But Ankur, since there's been a lot of interest on this topic, I don't know if Lane or Sam would be able to add any general comment on the interest of this topic from DoD Enterprise.
Okay, so some general comments, since I was a program officer at the National Science Foundation before my current position. The question really comes down to what kind of research are you trying to do? Are you trying to advance AI, or you advance a certain problem? So NSF is famous for funding high-level research. So here's good techniques that advance the world's knowledge. So if you're interested in exploring new AI techniques, etc., that's a natural home. So speaking very generally, mission agencies have, as the name implies, a mission. And so they're interested in solving real problems. And they're more not interested in the techniques that are used as much as the results. So if I want to check to see whether a piece of hardware is counterfeit or Trojaned, I'm interested in the results of it. And in some respects, the techniques underneath the inside the black box don't really matter. So if you're So they could be AI, they could be something else. So when selecting where to look at it, are you interested you should ask yourself, are you interested in the techniques themselves, or are you interested in a certain application? And if you're interested in a certain application, are you willing to say, okay, AI actually isn't that useful, but I'll use some other methods to solve this important problem?
Thank you, Sam. That's very helpful. I think, as Ankur mentioned, we can move forward with some of the other questions. Ankur, do you want to take any of them? Which one?
Yes.
Pick?
So there are a couple of, sorry, was somebody commenting?
No, there are two questions in the Q&A window right now, and there are, of course, a lot of questions in the slide.
So let's pick something from the slide, shall we? So,
yes.
And then we can come back to these questions in a minute. The larger, okay, so should I just pick something randomly, or?
Yeah, Ankur, if I may, maybe you can pick the next one. One question the couple of industry attendees came up with is that hardware assurance is definitely very, very important, but they said nobody wants to pay the price for assuring hardware. If I have to design in a solution, or if I have to do an extra step of verification, that comes at a cost. Now, they asked this question, who will pay the price for the assurance? Anyone would like to take?
So I can take the first stab at it. My first answer is yes, and my second answer is everyone. And the reason is at least from a DoD and even a national security infrastructure perspective, these are going to be requirements to have assurance, increased fidelity, lower risk, assured technology solutions coming into our supply chain. And so, the DoD will probably be leading the way with other commercial entities to provide that as a mechanism to build our systems. The challenge that we're going to face is that you have those like Vivian and her team that are highly risk adverse, who are going to want to have every T crossed and I dotted in their systems, which means they're going to spend the time to do the detailed analysis. If they can accelerate that or run more analysis because of AI and machine learning, they're going to do that because they're critical systems. And then on the far end, the other far end of the spectrum, we're going to have those that are interested in using disposable systems that are low cost and can still achieve a mission in a very effective way, but they may not want to incur the same cost burden of having all the T's and I's dotted in that system. So we'll be looking across the spectrum, and I think what will happen is there'll be the early adopters that will kind of lead the pathway, and then you'll start to see the other systems or others start to build that into their systems, because there'll be a discriminator of using those products within the high volume marketplace. So in essence, everyone will pay, and it will become a standard practice.
That's very well said, Len. I think we can move ahead with the next question. Ankur, feel free to pick one.
So I think we should go with 7. I think the question is, what are the problems where AI is not necessary, right? Do we really need AI when we have a good understanding formulation of the problem, or we have already the tools are strong enough to address some of the scalability challenges that we face? Any thoughts? Mike, maybe you can start, given the fact that you're from Synopsys.
Sure. I think there are lots of systems where AI is not necessary. You don't need AI in your microwave oven. You don't need it in your washing machine or
What are you talking about? AI is, I mean, I was going to buy the next generation of AI-enabled microwave. That's exactly.
Mike, how am I going to get my
that's-
popcorn like exactly right and
I
I know.
not burnt?
See, these are the kinds of things that drive consumerism, and I should be advocating for that, because disposable electronics is what the entire consumer electronics industry is built on. But in general, if you have a solution for a problem that's already highly optimized, it doesn't make sense to reapply AI to it. I think the systems that we need AI for are exactly the kinds of things that people like Len and Vivian have been talking about. You want to use AI to augment the capabilities of people and to do what people do badly. And, wringing the last cent out of my microwave oven or my washing machine and the use of water and everything else, and that is not necessarily the best use of an AI. The other thing is that AI just keeps solving the same problem over and over again, and so that can be done much more efficiently in terms of area and cost and even power consumption, especially your energy use, than a lot of other solutions. So I'll leave it at that.
Yeah, I'll just jump on what Mike was saying, and use the microwave as an illustration. Even if the microwave had AI built into it, the cost margins there are so slim and small, it's not going to be implemented very well, correctly, and it only leads to opportunities for someone to corrupt or take advantage of that system. So the cost dynamics still need to be taken into consideration when you're putting in a system, an AI system, and whether there's value in adding it to that operation.
But that's not going to stop somebody from doing it, Len.
I completely agree, but there'll be plenty of research articles written about how someone hacked it thanks to the AI being.
Yeah, that'll be 2 years after, and all the money's already in the bank.
Okay, the time is quickly running out, and we need to move fast. There are 3 more questions in the Q&A panel, Q&A window. So, John, if you don't mind, we'll take the other question by Subrata Kumar Devnath. He's basically asking, can AI be used to identify overproduced electronics, particularly to deal with counterfeiting and cloning problem? Any quick response to that? Mike, if you can comment on using.
Okay, I'm feeling
power.
pretty overexposed here. I'm very naked. I mean, this actually is a great question, because it's one of the things that people are trying to do is take advantage of this distributed knowledge that you get out of all of the data is measured, both through production and increasingly for systems that are fielded. And you're now starting to see almost fab-like metrology built into the chips that gives you ways to measure things about how the chip is behaving and what it's doing at a fairly granular level, that allows you to identify, all kinds of different things about either ways to optimize its use to make it more efficient, to make it use less energy, or to actually detect things like attacks that might be evolving, because you can see things about the activity inside the thing. And so this collection of data, if you can apply pattern recognition and pattern matching to it, gives you opportunities to do all kinds of things, from increasing security to making it more efficient, to reducing the ability of people to take things out of the fab and put them into the gray channel, or to recycle used parts and represent them as new. So I think those are, things that I see as opportunities for the future that people are not yet addressing. They're starting to try, but I think there's going to be a huge amount of development. This is one of the things that I think is a great opportunity for advancement.
Thank you, Mike. So Ankur, do you want to take the 2 new questions that came up? Ankur?
Yes. Okay. So, Kaylee Rice, what is potential for the advances in trusted AI and ML to be both applied to some of these problems and also perhaps uncover issues we weren't aware of? So, I guess the question really is that if you look at the recent advances in trusted AI and ML, perhaps, I mean, there's so many advances, we probably need to be a little bit specific, but I mean, are you aware of some of the recent advances, adversarial machine learning, generative adversarial machine learning, for example, to create scenarios that you haven't seen before, or adversarial inputs, which is a different problem, to sensitize machine learning models in areas that they are brittle. These are two examples that I can think of. Do you see any of their relevance to some of the problems related to hardware and AI?
So I think, Ankur, probably the question that we should try to answer is that, can AI detect unknown unknowns, something which we are not aware of? So let's see if the panel can make some.
That is probably a better way to put it.
Yeah. So we've done some research in looking at how to use AI machine learning to basically do attacker defender scenarios that helps us identify areas that need to be secured more effectively, or whether our strategy was effective, and let the engine kind of play out the game. So there we're looking at it from a different perspective. We're applying AI machine learning in a way that, you know, we would not be able to play out all the games effectively by ourselves as individuals, but using the systems to kind of play out those scenarios. In those cases, it would illustrate things that we would not have been able to find in our normal operation.
Thank you, Len. We are running out of time. Ankur, we have a lot of questions. I don't know if we can take any of them. We have actually 6 minutes left.
So maybe we can ask all the panelists, and this time we'll go in reverse order, to provide maybe a closing sentence on what they think about the future of this field, especially in the context of the relevance of AI and the pitfalls of AI in the context of hardware. Does that sound like a good plan, Swarup?
Yes. Let's go ahead and maybe in 1 minute, each of the panelists can give that perspective about the future of this field. Yes, maybe we can start with Sam.
Right. So let me go to Sam. Sam, 1 minute for you, sir.
Okay, so I think I'll just reiterate that AI should be considered as an end in itself, but you should concentrate on what it brings to the table. And I think there's AI can do a lot of things that people are naturally bad at, and we should just try to emphasize what it's useful for and not think of itself as a replacement for good engineering or a magic bullet.
Thank you, Sam. Len?
Yeah, so I completely agree. It's not going to solve all our problems. So I'm not going to reiterate that. I did want to let people know that there was a National Artificial Intelligence Initiative that was launched by the White House. There's opportunities there. There's also AI and machine learning is on the DoD modernization priorities. There's opportunities at Office of Secretary of Defense for research and engineering. I think the question will be, how are you applying AI machine learning? If you can contextualize it in a way that they can understand and apply it to microelectronics, there's a good shot for funding. And like I said, our team is also looking into that in more detail and using as a mechanism, a tool in our belt that of many tools to execute our mission.
Thanks a lot, Len. Brian?
Yes, AI certainly should be applied to really improve the speed, precision, and effectiveness of human efforts. And really, the cornerstone for responsible development and deployment should be the following: that AI systems should treat all people fairly. They should be reliable and safe, secure and respect privacy, empower everyone and engage people, and fundamentally be understandable and explainable. Ultimately, people should be accountable for AI systems and tools that are deployed at the end of the day. So thank you, and certainly look forward to the next CAD for Assurance event.
Thank you, Brian. Vivian?
Thanks. So one thing we learned about capital T trust is it's really, really expensive not to have it. So if we're not making friends with AI, then we're falling behind. But if we're going to have this framework where we incorporate it into hardware assurance, then there needs to be some scaffolding. There's going to be some checks and balances. So in this new role I have in the cyber systems assessments area, I'm really going to be looking for that pathway where it's not just supporting the research, but finding a way that we can bring it to day-to-day practice.
Thank you, Vivian. And Mike, you're last. Mike,
I think this works better if I'm off mute. So I think those points were great that people made throughout the course of this, and there were some excellent questions. John Barris seems to be on fire today.
He's always on fire, trust me.
Okay. Well, anyways, we there were a lot of questions we didn't get to today, but I think I'll leave you with one challenge as my closing thought, and that is to pick up on what Brian Knight and others have said about responsible AI and AI in the service of humans. And the challenge is this. It's great to say that. It depends on goodwill of virtually everybody who's working in the space. And I think that's virtually impossible to assure. And so the challenge is, what are you going to do, or what can be done to systematize this and actually build it in? Because the so-called 3 rules of robots don't work.
Thanks a lot, Mike.